Here we are, the last episode, and we get to spend it building one thing out of everything we have made. The task is the oldest one in language modeling. Predict the next token from the ones just before it. Here is a stream of characters, and we draw a box around the last few of them, the context, and we ask the model for the token that comes next. Nothing about this is new to you. We have a network that turns an input into a distribution and learns from its own gradient. The only question is how we hand a few tokens of text to a network that only understands numbers. The oldest answer is to count. Walk through a big pile of text, and for every context you see, keep a tally of what followed it. To predict, you look up the current context and read off the counts. It works right up until it does not. Look at the tallies. A short context like the word that has been seen thousands of times, so its tally is rich. But stretch the context to the last several characters, on the ma, and you will find you have never seen that exact run before, not even once. The tally is empty, and the model has nothing to say. The longer and more useful the context, the more often it has never occurred. Counting drowns in the combinations it has never met.
So the problem is that every context is treated as its own separate box, with nothing shared between them.
Exactly that. Counting has no idea that two contexts are similar. The cat sat and the dog sat are, to a table of counts, completely unrelated rows. A network can do better, because it can learn that cat and dog behave alike, and then what it learns from one helps it with the other. That sharing of statistical strength across similar contexts is the whole reason to reach for a network here. And it turns entirely on one new idea, the way we represent a token. The one new part is called an embedding, and it is almost embarrassingly simple. It is a table with one row per token in the vocabulary, and every row is a short vector of numbers that the network gets to learn. The forward pass is just a lookup. Given a token's id, an integer, you return that row of the table. Here is the real code. Append the id to a small cache so backward knows which row was used and return a copy of the weights for that token. That is it. To embed the token cat, we walk to the cat row and read out its vector. Mathematically, it is a linear layer applied to a one-hot input, but we skip the multiply by 0 and just index straight to the row. Backward is just as clean, and it is where the learning lives. When the gradient comes back for a token's vector, we pop that token's id off the cache, and we add the gradient into that one row of the table and no other. Look at the code. Pop the id, take that row of the gradient accumulator, and add the incoming gradient in, element by element. Every other row is left exactly as it was. The rows that were used get nudged. The rows that were not stay still. Over a whole corpus, each token's vector is shaped only by the times that token actually appeared. And that should feel familiar, because it is the same rule that has run through this entire series. A shared parameter collects a summed gradient. In the convolution episode, one kernel was shared across space, and its gradient was the sum over every position. In recurrence, one cell was shared across time. Here the embedding table is shared across the whole vocabulary, and each token's row gathers the sum of the gradient from every time that token was seen. Same idea, one more place.
So if the rows are learned, can two tokens end up with almost the same vector?
Yes, and that is the entire point. Picture the embedding space, just two of its dimensions drawn on a plane. Nothing forces cat and dog apart, so if the training keeps using them in similar ways, they can drift until their vectors sit close together. Now anything the network learns to do with the region where cat lives, it also does, almost for free, with dog right beside it. That is the smoothness assumption, the belief that nearby inputs should behave alike, and it is exactly the thing a table of raw counts can never have. It is why the embedding beats counting. One embedding gives us the vector for a single token, but the task asks us to look at a few tokens of context at once. So we wrap the embedding in a layer that Scratch calls embed concat. It takes the last few token ids, looks each one up in the same shared table, and then concatenates the results, laying the vectors end to end into one long input vector. Here is the forward pass in full. Reset the cache, then for each token id in the window, extend the output with that token's embedding, and return the whole flat list. 3 tokens, each a short vector, become one longer vector. That single vector is everything the rest of the network will get to see. And notice what that quietly decides. The window is a fixed size. It holds the last few tokens and no more. Anything that happened before the window simply has no wire into the network. It cannot touch the prediction at all. Back at the start of the series, we would have written that as a rule about probability, that the next token depends only on the last few. That is the Markov assumption. Here we do not state it as a rule, we build it into the shape of the input. The assumption is not written in the math, it is welded into the architecture. A fixed window is the Markov assumption, made out of code. This exact design has a name and a date. This is Yoshua Bengio, and in 2003, he and his colleagues published the Neural Probabilistic Language Model. Embed each token in a fixed window, concatenate, and run the result through a small neural network to predict the next word. If you followed the Inductive Biases series, you have met this model before. There we read it from the outside as a set of assumptions. The window is the Markov bias, the embedding is the smoothness bias. Here we are on the inside. We are not describing the assumptions. We are building the layers that make them true, and in a moment, we are going to run the thing.
So after all that, how much new code does the actual model take?
Almost none, and that is the payoff. Here is the entire model, written as one of our plain network objects. Embed concat turns the window into a vector, then a linear layer, then a hyperbolic tangent, then another linear, wrapped in softmax cross-entropy over the vocabulary. Look down the right side. Embed concat is the only piece we built today. The linear and hyperbolic tangent stack is the multi-layer perceptron from episode 4, built from the linear primitive that goes back to episode 1. The softmax cross-entropy head is from episode 3. There is no new machinery here. A language model is not a different kind of thing. It is the parts we already have, stacked in the right order. Let us watch a single input flow all the way through. On the left, 3 tokens, the characters T, H, E. Each one is looked up in the embedding table and becomes a short vector. Those vectors are concatenated into one longer vector. That vector feeds the multi-layer perceptron, a linear, a tan, and a linear, and out the far side come the logits, one number per token in the vocabulary. Softmax turns them into the bars you see on the right, a real probability for every possible next token. And these bars are not a drawing. This is a genuine forward pass through the exact architecture, computed live, the same arithmetic scratch and runs. There is one honest thing to point out about those bars. Right now they are almost flat, every token about equally likely, because this model has not been trained. Its embedding rows and its weights are still random. A flat distribution is the correct answer for a network that knows nothing. Training is what carves it. I ran a small fixed context LM trace on Alice with context length 6. The loss falls from 2.8683 to 2.3279 in 3 epochs, and after the context Alice space, the next character distribution is no longer flat. H and T are now the leading choices. Sampled after that run, it produces fragments like Alice was Thiel Bitzenthelp. Not fluent, not clever, but real trained behavior coming out of a table of vectors and one small perceptron that we built by hand. Before we call anything finished, we do the one thing we have done at the end of every episode. We check the gradient. We build the language model, hand gradient check a context and its target token, and let it work. It perturbs every parameter by a tiny amount, the embedding rows very much included, measures the loss on each side, and takes the central difference. Then it compares that numerical slope against the gradient our own backward pass produced. And they agree to about 1 part in 10 million. The embedding, the concatenation, the whole model, all of it, the green card, one last time. We did not trust a single gradient we could not verify. So let us step back and look at the whole road. It started with 1 unit and the residual, the prediction minus the target, in episode 1. Episode 2 turned that seed into backprop, the gradient walked backward through the layers. Episode 3 widened the output into softmax. Episode 4 stacked layers into a multi-layer perceptron. Episode 5 made the head explicit: binary, categorical, real-valued, count, and uncertainty. Then Episode 6 shared weights across space with convolution. Episode 7 shared them across time with recurrence. And here, Episode 8, we assembled a language model. 8 episodes, 1 line. Every layer along it is pure Python, and every gradient was checked by hand against finite differences. No autograd, no mystery, nothing we did not verify. Where does it go from here? This model carries only a fixed window, the Markov assumption we welded in. Recurrence already loosened that, letting the past flow through a hidden state instead of a hard cutoff. The next step lets positions choose which past positions matter. That is attention, not just a longer window, but content-dependent access to context. It deserves its own from-scratch story, in the same layer-by-layer style. For now, you have built a real language model, out of parts you understand all the way down. Thank you for watching, and thank you for building it with me.